In the last lecture, I was talking about pore size distribution and I discussed the algorithm for the evaluation of the properties or thickness of the pore, rather the adsorbed layer thickness and the pore size distribution, which was a cumulative pore size distribution or the change in pore radius as a function of pressure. So, as I said that we have the data in the form of P by P 0 versus volume adsorbed, right. So, this is the experimental information which can be determined from the PET experiment, right. So, at different pressure, by increasing the pressure to a saturation pressure, the volume of the gas adsorbed is measured and you can plot, and this can be used to determine the BET surface area also, right, and average pore radius, average pore size, what I talked before. But if you want to get the in depth pore analysis, pore size distribution, you need to look at the T plot, right. So, you need to find out the thickness, adsorbed layer thickness, which we have talked last time, right, based on Wheeler's model, and the Kelvin radius. So, that also we talked in terms of the vapor pressure release equation or Kelvin equation. So, R k is the Kelvin radius here, right. So, this Kelvin radius, as I said, is less than the actual pore radius. So, that is to be added. So, you get the pore radius here. So, this is your actual radius of the pore, or which is used to determine the pore size distribution, or that takes part during the catalytic action, right. If you want to get further analysis, you can find out the difference for between two pressure difference, what is the difference in the volume desorbed, because we are talking a desorption data here, and simultaneously what is the decrement in the condensed layer thickness, right. So, that is delta T. So, which can be obtained between two successive thickness, layer thickness, and you can find out these delta T, right, which is related to your decrement in the fractional volume, right, because in that delta T layer, what is the volume of the gas liquid which is desorbed, right. So, that can be calculated. So, that we have seen based on that per meter square the nitrogen has 0.23 centimeters cube volume, and then you can calculate it based on that, assuming 16.2 angstrom square is the area of one nitrogen molecule. And then you can find out change in the Kelvin, that is the pore volume, which is because of the Kelvin radius the volume of the liquid desorbed. So, that is nothing but calculation of the total pore volume minus volume of the liquid which has been vaporized from the adsorb, that is delta V f, right. So, that can be calculated. This can be related to your pore volume, because I told that pore volume is related to the pore radius, right. So, delta V p upon delta V k is equal to R p upon R k whole square, right. So, that delta p is nothing but pi r square, pi, that is the volume of the pore into cross section area of the pore into length. So, pore volume, if I say area of cross section into length. So, pi r square into length, right. So, cross section area pi r square multiplied by length. So, length of the pore is same. So, you can just very easily correlate delta V p and delta V k. So, which is given here in terms of this multiplied by that square of the radius, that is R p over R k whole square. So, you can very easily calculate that, and then you can also calculate this change in the surface area, right, BET surface area, which you have calculated. So, between two successive delta p, what are the number of molecules, gas molecule which have desorbed from the surface, and area of one molecule is known. So, that is the decrement or change in the surface area of the molecule, gas molecule. I am not talking in terms of now surface, right. So, but that is equivalent to the layers or delta T, that is equivalent to your delta T also, right. So, we get total surface area. So, that is just similar to your BET surface area, but for corresponding layer thickness. Finally, if I look at this value, you see here it is almost a constant value. So, this is the surface area of that solid, which is similar to your BET surface area, if you calculate from that, right. So, total number of molecules which have desorbed from the surface, and that is related to the surface area, right. Then there are some additional information, this delta V p L which is written, that is corrected because you calculated at the adsorb condition, you can convert it into the STP conditions. So, just correlated with the density of the gas and density of the liquid. So, this is the ratio of density of the nitrogen gas divided by the density of the liquid nitrogen, right. So, that will give you nothing but the volume or standard condition. And finally, this is your cumulative pore volume, right. So, volume, that is what you have total nitrogen, which is that is the gas molecule or adsorbed molecule which have dissolved from the surface, right, as a function of P by P 0, which I have shown before. So, this is a kind of cumulative plot, right. So, 0 to 91.2, right. So, that is the total volume of the gas dissolved, and you can plot it. So, you can have a delta V from here, right, as a function of pore radius R P, which we have seen, right. So, delta V upon delta R, which I was talking a pore size distribution. So, now you can have a plot from this, which can be in terms of d V over d R, right, between two successive pore radius, and this can be as a function of pore size, right, as I said earlier also. So, this can be a function of pore radius, which I am talking here A or R P, right, total pore radius. So, this is between two successive pore radius. So, if I am talking a pore size distribution, so which is related to your P by P 0, if you look at here, right. So, this is your pressure which is higher in this side, right. So, where the smallest pores are also filled, right, and this, so that time it will be your total pore volume, right, and that will be your the smallest pore which has been filled, right, and starting from the largest pore. So, first larger pore get filled and then small. So, desorption takes place first when you talk the from the largest pore, right, because it is related to the radius. So, vapor pressure in a small pore, so that will fill first, right. So, pore filling is first in the small pore, but when you look at the desorption, then again it will be, because it is inversely proportional to the radius of the capillary, right. So, the pressure is released, so immediately the pore will get vacated, and that is the region you get a kind of hysteresis during this, right. So, this dV upon d log A, what we are saying, will give you a cumulative pore size distribution and sorry, this pore size distribution. So, this is your pore size distribution, right. So, nothing but just this, you take these two delta V, you just take two delta R between two corresponding radii, right, and you can take this, or sometime you will see it like this also, dV upon d of log of A, right. So, if I just plot it like this pressure, I can have a P by P 0 value also, or just as a function of pressure, and then if I am writing pressure increasing in this, so probably the radius will go in this side, right. If your radius is increasing in this side, then pressure will come here, right, because the higher pressure means the smallest pore size, right. So, that is, it means if I am just talking a cumulative pore volume, then it will go again something like this, right. So, it will go like this, something like this, right. So, that is the total pore volume if I write in terms of pore volume distribution, and this is something like where the largest pores gets filled, right. So, that is it, in that case the all the pores are filled here. So, this is the highest pressure, right, and here the pores are smallest pore. So, this is total pore volume, that is all the pores are filled from this point to this point, right. And when I say cumulative pore size, this is your cumulative pore size distribution, that is cumulative plot right related to the pore volume, but this one is the pore size distribution. So, this gives you the idea between two radii. If I write like this, so this is your, as I said, this is the smallest pressure. So, this is the pore larger. So, this will be A plus delta A here, right, and this is A. So, this, that is between two radii A and A plus delta A, what is the pore or what is the volume of the pore which has just filled, right. The total pore volume between two radii, if I just say that, suppose this is your 100 angstrom and this is your 1500 angstrom, right. So, I can have the idea that between two pores 100 and 100 1500 angstrom, what is the volume of the pore which got filled, and that is your delta V, right. So, this is known as your pore size distribution in a catalyst. So, whether in a catalyst you can have a just narrower pore size distribution, right, just like in a zeolite catalyst you see, right, molecular sieve catalyst you see, it can be wide pore size distribution like in different kind of activated carbon material or alumina materials, right. So, wider pore size distribution, it may have only the micropores like in zeolite what you see macropore and mesopore, or sometimes it can have only the macropores, which is nothing but between the particles, right. So, there the particle itself one particle, if I look at fine particle, that may be a non-porous material, but when you make a pallet from that, right. So, that is nothing but the pore space between the particles, right. So, that will be kind of macro pore, and depending upon the pressure, as I said, when you make a tablet from that, you apply the pressure. So, depending upon that pressure, you get different kind of pore size distribution, right. So, the molecular sieves or extrudates generally, where we want that the pores should be sufficient, it should have large surface area. So, recommended is that you draw it, you make the extrudates rather making a pellet, right, because the extrudates will have larger porosity, but the problem is that you have to balance it between porosity and the strength, mechanical strength of the pellet, right, because the extrudate may not hold that larger pressure, especially in a fixed bed reactor or when you have fluidized bed, attrition of the particle may arise, right. So, these things has to be checked. So, again I was talking a kind of hysteresis also, right. So, now you can have some idea that why hysteresis forms, right, that is what we talked, that because of the pores may not be closed from one end, right, the pores are open from both ends, because the hysteresis you will not get when the pores are straight cylindrical and closed from one end, right, because the meniscus forms. So, basically the meniscus formation is related to the hysteresis, right. So, when there is a formation of meniscus, hysteresis will not form, but when there is a delay in formation of the meniscus, depending upon the shape of the pore, then you may get the hysteresis, right. So, what is the meaning of hysteresis? That is related to the Calvin equation, right. So, when you are applying pressure, the adsorption is taking place, right. So, the lower pore will fill first, right, or whenever capillary which has smaller size, that will get filled, but the larger one, something like a ink bottle, old fashioned ink bottle, if you look at, the larger pore may not get, right. So, when the desorption takes place, what will happen? Because you know that desorption is again when you are releasing the pressure. So, at the same pressure where the adsorption takes place, where the condensation start, the molecule may not leave the surface, right, because it is stable, you have to make it unstable, right. So, that radius of the neck has to be unstable for relieving the gas molecule. So, you may relieve the pressure more, or you have to release the pressure more, right, then the desorption will start, right. So, that is the region of hysteresis. So, what we have talked last time also. So, I am just showing this slide for hysteresis formation, which is similar to that what we discussed, that is the neck fills at a lower pressures, right. When you have a narrower area, narrower volume, narrower radius of the that neck or pore, then the condensation will start, right, in a smaller pore first, that is what I said, right. So, this is related to your Calvin equation, which is same equation. So, this is the pressure required for adsorption in a pore is equal to the whatever the saturation pressure times exponent of minus 2 sigma V divided by R B R T, right. So, this is your Calvin equation, what we have seen earlier, right, in terms of log scales. So, that time it was log of P by P 0 is equal to minus 2 sigma V upon R B R T. So, V is the volume of the liquid adsorbed, R B is the radius of that capillary, right. So, this is PA, adsorption pressure, which is related to your radius of that capillary, right. Now, when there is a desorption, right. So, desorption will take place because smallest pore, right, and the bulk has the larger size, the volume is larger, right. That is I am talking just like an ink bottle or this kind of system here, system something like this, right, or it can be like this also, the shape something like this, right, and these pores are open from both ends, right. So, problem is in terms of meniscus formation, right, which will form easily in the case of the closed end pore, right. That is a kind of wetting the surface, because you are talking a contact angle 0, right. So, it wets the surface. So, meniscus forms there. So, here this is the pressure for adsorption, and when desorption starts, so you will write the pressure required for desorption P d, right, and this pressure is again equal to the same equation, that is P 0 exp minus twice sigma V upon R n R T now, because the desorption is will take place from the neck first, right. The pores are filled when the adsorption has taken place, right. So, because the neck has lower radius and the lower portion has this larger radius. So, it means the desorption will take place in this according to this equation, right. So, now this neck radius is less than the bulk radius, right, or the actual pore radius. So, this is what the radius of the neck R n is less than R b. So, what will result? The pressure for adsorption is higher than the desorption, right, same equation, just take the ratio, right. So, adsorption require the pressure will be higher, right, to adsorb a given volume, right, but when you want to relieve that volume, you need to release the pressure to a larger extent, right. So, what does it mean? This simply means that at the same condition of pressure here, if I just look at this point, this was the pressure required for adsorption, right, where the volume adsorbed is this. Now, here when the desorption started, at the same pressure, now larger volume has desorbed, right, or to relieve the same volume, a lower pressure will be required, right. If I just look at this point which is equivalent to the same volume, this much pressure will be required. You have to release, because you are talking desorption, you have to relieve the pressure, right, and this is what called either the incubator effect. Because of the incubator effect, it can be layered structures also, right, it can be the region that pores are open from both ends, right, not straight cylindrical. So, all kind of complex geometry of the pore can be looked into once you have this desorption isotherm, right. So, by having this plot, that is pressure or volume versus P by P 0, you can have the information in terms of this hysteresis, adsorption hysteresis what you call, right. So, given volume which is here is desorbed at a pressure lower than that what is adsorbed, right. So, that is what you call the adsorption hysteresis. So, there can be A, B, C, D, E different 5 types of adsorption hysteresis have been observed experimentally depending upon the type of the solid material. So, that is what I said, that the structure may be of different nature, hexagonal like this, right. It can be this rectangular channel and it can be ink bottle type, but ink bottle also here this radius, this length is larger compared to this neck length. So, there can be a different kind of hysteresis in the other system. So, what I have just discussed is here that adsorption and desorption branches are steep at intermediate relative pressure in tubular capillaries open at both ends. So, this what you have seen type A, it is somewhere at the intermediate, but it can start from here also in some of the materials, right, that is known as type B type adsorption hysteresis. So, which are open from the both ends, because this comes at an intermediate pressure where the hysteresis is observed, right. The tubular pores close to one end do not show hysteresis at all, as there is no delay in the formation of meniscus on adsorption, right. So, this desorption is related to the curved structure which is formed on the surface. So, when there is a pore which is closed from this end, so you will have a kind of this meniscus. That in open you will not have that kind of meniscus, it delays, and that because that is the region that you do not get. If the pores are closed from one end, you will not get any hysteresis. This is another type B, where you can see that it has reached to the saturation pressure, right, higher, that is P by P 0 approach to 1, and then the hysteresis is forming, whereas in that case earlier case it was the intermediate at some intermediate point. So, that is what I am saying that, and this will be seen in this kind of structures, layered structures, right. So, if the pore is formed by two parallel plates, right, lamellar type, a meniscus cannot form until the vapor pressure of adsorbate is equal to saturation pressure. You have to go with a very high pressure, right, because it is a slit type structure, right. On desorption, the pore is emptied at a relative pressure corresponding to the width of the capillary, which is effective radius of the curvature of the meniscus, right. So, this time the width of capillary is equivalent to the equivalent radius of the capillary, right, not the gap, right. So, width of the capillary which is effective radius of the curvature of the meniscus. So, this simply results the isotherm has steep adsorption at a relative pressure of 1 here, something like that, and the reason for desorption is that the meniscus formation is delayed, right. So, and at it goes to the saturation pressure. So, P by P 01. So, what I mean to say, depending upon the type of material, you can have the different kind of complexity in the pore structure, right, or results what you see, the pore size distribution or the hysteresis of that. So, that is again you can see here this gap is also wider, right. So, it means when it reach to the saturation pressure, and if you look at the two corresponding pressures here and here, right. So, if I just look at the same volume, significantly high pressure reduction is required, right. You have to release the pressure to a significant low level, right, then only the desorption will start. So, and the results, because the adsorption layers may not be correct in terms of Kelvin radius, right, because your desorption is related to the capillary condensation, and from there the desorption takes place. So, generally the correct results are from the desorption. When you calculate the values of surface area pore size distribution, then desorption values are taken as a final result, right. So, all these materials like graphite oxides, montmolinites, clay type structures, aluminum, hydroxides are crystalline, and packing of particles in lamina gives open slit shaped capillary with parallel walls, right. So, this type of the structures will have your type B adsorption hysteresis, right. Similarly, the ink bottle pore with a wide body which has more pore size wider than that is 1000 angstrom approximately, then also you will have a kind of this hysteresis, right. So, this structure is different compared to the first one here, right, this structure. So, this one, right. So, here this is very large and this is relatively low compared to this case where it is larger, right. So, the hysteresis will depend on these kind of structures or geometry. So, that is the case of physical adsorption. So, you have seen the BET surface area, right, and then determination of pore size, pore volume, thickness of the layer, adsorption hysteresis, right, based on the nitrogen adsorption desorption isotherm, and that is the case of physical adsorption, right. So, that just talks about the textural property of the catalyst, right. Morphology, there are some other methods by which we will talk on that. Morphology can be evaluated in terms of spherical shape or particle size, right, the crystalline size, crystallinity. So, there are other methods also which we will talk on that based on the X-ray diffraction patterns, and here now I am talking the chemisorption, right. So, it means some reactive gas which comes, right, and adsorbs on the surface of the active metal now. So far the adsorption is throughout the surface, whether there is the active metal or not, adsorption will take place because it is the condensation of the gas molecule, and you said that it is the physical adsorption, right. Here what we are talking, this is specific in nature, only a reactive gas, which a type of reactive gas will adsorb specifically on a surface which is active for that gas, right. Otherwise, there will not be adsorption. So, this is what I said, that chemisorption requires the higher amount of activation energy compared to the physical adsorption, that we have already seen, right. So, but this is very important tool for the determination of the chemical behavior of the catalyst, right, and that is related to your catalytic activity. So, we can have the same reactive gas also which is being used in the reactor for further investigation, can be used as a chemisorption study also, right. Turnover frequency, turnover number which you determine is based on this study. So, this gives you the specific surface area of the phase edge, now I am saying, right, because it is a chemical adsorption. So, specific surface area of that crystal which is active for the reaction, right, not the physical adsorption. So, physical adsorbed surface area may be very high, 200 to 20 meters square per gram, but this area may be just 10 meters square per gram or 5 meters square per gram, right. Also it gives you the idea about the active phase, right. So, which phase is active during a catalytic reaction, you can get the information from this, right. You can just make different catalysts, you can just give the different treatment and then look at their chemisorption property. Then number of active sites, that is your what you talk dispersion, right, and then you calculate your turnover frequency. So, you can get the number of active sites, right. reactivity of active site, you can do the Kamijoffson at different condition of temperature, right, and then you can talk on the reactivity also, or you can calculate the activation energy also from this kind of study, right. And then stability of the active sites, which is again important for the catalytic activity, that is stability of the catalyst, right. So, for how much time the catalyst can be used, or after regeneration it can be recycled back into the system. So, these kind of investigations may be made or can be done from this Kamijoffson study. So, what is Kamijoffson? All of you know, but quickly I have discussed this thing earlier, that the purpose of this Kamijoffson technique is to disperse a catalytic components to maximize their availability to reactant. So, generally when you prepare a catalyst, right, your aim is to have high dispersion of the metal, right. So, metal disperse on the surface of the solid. So, how good or how bad they are distributed onto the support, that is the first information you can get from Kamijoffson. So, we want to maximize the availability of these metal species for the reactant, and you know that, or you should learn this also, that highly crystalline material may not be good, right. If your XRD pattern gives you a large number of peaks, does not mean that it is good for catalytic activity, right. You need to have a fine dispersed particle, very small particles, crystallites and nanoparticles, right, and that may not be visible from XRD pattern, right, and but may be very good for the catalytic activity, right. So, this is also important, that when a structure has a definite XRD pattern, it usually has less than optimum activity, right. So, because we need more and more defects on the surface, right, to have a good catalytic activity, right, edge structure, right. So, not necessary that your material is crystalline for a good catalytic activity, it can be amorphous also, right. So, you know that this is because most of the catalytic reactions are favored either amorphous material or extremely small crystallites. So, if you are developing the crystal size should be as small as possible, right, and when you have a small crystal size, then they may not be detected by the XRD analysis, right. So, crystalline material may not be good, or degree of crystallinity may not be related to the catalytic activity. So, we talk dispersion, which I already defined, that number of active sites on the surface divided by the theoretical number of sites which are present on the total number of sites which are present, right. So, theoretical means which you have calculated for the preparation of the catalyst, right. You have prepared 10 weight% of platinum on alumina, right. So, it means you know that should be the theoretically present, and also should be confirmed by some characterization method like atomic absorption spectroscopy, right, or inductive coupled plasma ICP technique, right. So, that will give you the actual number of the metal which is present on the catalyst, right. So, one is from your initial calculation, but during the heat treatment there may be some loss. So, you get it confirmed from some chemical methods, right. So, ICP is one, atomic absorption spectroscopy or UV spectrophotometer can be used, right, you can find out those. So, that is your theoretical metal concentration. Actual concentration now will be which is related to the catalytic activity and from Kamijoffson. So, this number of active sites on the surface are actually the sites which will be responsible for catalytic activity. So, if you have 100 metal species on the surface, 100 atoms, right, out of that 10 may be available on the surface, and these 10 will give you the catalytic activity, remaining 90 is a waste, right, and that is why the atom efficiency what we talked in the concept of green chemistry becomes important when you look at the catalyst preparation, right. So, instead of having 10 weight% of the platinum, try to have 0.5% of the platinum with more than 90% dispersion or more than 70% dispersion, that should be your target, right, to get good efficiency from the small concentration which is used, and every site should be active for the catalytic reaction. So, dispersion becomes very important, and this is based on the turnover frequency also. So, from this you calculate the turnover frequency, right, that is number of molecules which have reacted, right, per unit time, right, and per unit active site which is available on the surface. So, you can put that dispersion here, right. Total number of sites multiplied by dispersion will be nothing but the sites which are on the surface. So, if you have done that effectively, if the dispersion is good, only small crystals are present and the diffraction of X-ray is minimal, right. So, if the particles are finely dispersed, your particles are of the order of say nanometers, right, small the crystallite size, they are better dispersed, X-ray will not detect that, right. All the species may not be detected, right. See, either because of low concentration or because that the crystallite size is so small that X-ray, because wavelength is important for that, right. So, X-ray what is the wavelength of that, and then accordingly you can calculate that, right. So, when you have this, so selective chemisorption can be used to measure the accessible catalytic component on the surface, that is dispersion, right, by noting the amount of gas adsorbed per unit weight of the catalyst. So, it is similar to your physical adsorption here, right. The only thing that now we have a chemically reactive gas. So, this will adsorb only the active sites of the surface. So, how many molecule of those gas species or that gas species adsorbed on the surface, the volume of that gas can be measured, and that volume can be related to the number of atoms, and you know the atom area. So, you can find out the surface area, right. So, percentage of metal dispersion on the surface can be find out. So, when you look at chemisorption, it is a kind of chemical reaction mechanism, right, which we will see in detail later, but this is a support on which the metal has been deposited like this. This is your metal, and when the gas species which may be hydrogen, which may be carbon monoxide or carbon dioxide or nitrogen oxide, N2O, any gas can be used, reactive gas. So, gas phase diffusion, right, CO is coming here like this, and this is what is here just shown a molecular adsorption, right. So, I will talk that later also. So, the CO molecule as such is adsorbing on this, sometimes it may be dissociative also, right. So, a combined molecule of carbon monoxide, this adsorbs on the surface, right. If it is dissociative, then it could be something like that, carbon monoxide will split first and then it will two carbon and oxygen, and then they are adsorbing, right, just like in the case of oxygen it is shown here, right. So, oxygen is split it into two. So, one oxygen here and one oxygen here like this, splits on the surface, right. If I talk in terms of sites, it is covering two sites, two active sites, right. And then they are migrating onto the surface, because to have the catalytic activity, these molecules have to be mobile on the surface, right. So, this is because of the surface diffusion phenomena like this, and then this is the chemical reaction at the surface, product forms and then desorbs, right. So, this principle is similar, but like a chemical reaction here, just you can talk a CO oxidation here, right. So, you can find out that what is the actual mechanism depending upon the temperature, because this will be a function of temperature, right. So, at different condition of temperature, how many molecules are reacting, right, and then you can calculate the activation energy for chemisorption, right. Here right now I am talking just a characterization, not the chemical reaction like what I have shown before, that the rate of adsorption, right, you know that it is nothing but dN by dt, right, the number of molecules which are adsorbed on the surface, and that is related to some S sticking coefficient and times the flux, right. So, F we have already said earlier, right, we have already seen the calculation for F, which is just nothing but under 1 upon under root of 2 pi m k b T some, right, and into P. So, pressure related, right. So, that is in general you write your rate of adsorption R is equal to K rate constant, right, adsorption rate constant times partial pressure, right, and times the fraction of the surface which is vacant, right. Same thing is written here. The only thing that sticking coefficient S generally is given, we have assumed here almost independent for most of the case sticking coefficient, but generally it decreases with the surface coverage like this, right. So, S01 minus theta, and this F flux is proportional to the pressure. So, P upon under root of 2 pi m k b T, what we have seen last time in the flux calculation, right. So, in general you calculate it like this. So, if you just integrate this equation, so here it is S into F into T. So, I was talking the exposure time earlier, right. So, that is also important. It means your adsorption will depend or chemisorption will depend what is the flow rate of that gas, right, number of molecules which are coming onto the surface and for how much time. Time of exposure is also equally important, right. So, that is the total number of molecule on the surface will relate are related to the sticking coefficient or probability of sticking, right, and the flux multiplied by the exposure time. So, that gives you the idea of the surface coverage or chemisorption, that is the reaction number of molecule which adsorbed. So, once you have that V, that is volume adsorbed as a function of pressure, Langmuir isotherm, nothing but, right, we already talked that, because Langmuir isotherm talks a monolayer coverage. So, this is a kind of monolayer coverage here in this case, right. So, here it is the volume of the gas adsorbed as a function of pressure, and you will have something like B p upon 1 plus B p last time what we talked, or K p upon 1 plus K p, where capital K is the adsorption equilibrium constant. Rate of adsorption is equal to rate of desorption, right. So, this is a function of temperature and pressure, right, just like in the Langmuir equation now you have seen, right. So, Langmuir equation we have seen last time theta related to V by V m, a monolayer coverage, and that was K p upon 1 plus K p here, or B p upon 1 plus B p, where B is the adsorption equilibrium constant. So, B is simply K adsorption divided by K desorption, right. So, this equation has been used, and so always there will be a monolayer when you are talking a chemisorption, no multilayer will form, right. So, there is a monolayer, but this will be a function of pressure. So, pressure effect not shown here anyway. So, this is already shown here. So, theta, the rate of adsorption increase with pressure, right, that is the first thing, right, from this equation, adsorption increase with pressure, right. But how this B, which is the adsorption equilibrium constant, also how does it affect the adsorption, that is also that if you have increasing the K value or equilibrium constant, right, for adsorption, or small b, which is simply your adsorption equilibrium constant. So, increasing this, your surface coverage increase, fraction of the surface covered increase, right. So, rate in the forward direction is increasing in one way, right. So, that is the, if the equilibrium constant is high, then your surface coverage will increase. It is exothermic, most of the time the chemisorption is exothermic. So, it will always decrease with temperature, right. So, this is the effect of temperature. So, B increase when temperature decrease, and B increase also when heat of adsorption increase. So, heat of adsorption can be calculated from Clausius-Clapeyron equation, right. So, that can be used to determine the heat of adsorption. So, heat of adsorption, if B is higher, heat of adsorption will be higher, right. That K d over dt of ln K is equal to delta H upon minus R T square, that is equation, right, that can be correlated with this. So, this is what I was talking, Clausius-Clapeyron equation, right. So, del over or del ln P of divided by del of 1 by T, right, at constant coverage is equal to delta H adsorption divided by R, right. If you integrate this, you can just simplify the equation in the one top equation, or this equation nothing but d over dt of ln P is equal to minus delta H upon R T square, right. That equation is known to you. So, this equation correlates the heat of adsorption, or can be used to calculate the heat of adsorption. If your plot of log plot of ln P versus 1 by T, you will get a straight line, and from that you can find out the heat of adsorption, right, just from after integration, right. So, you can very easily find out this, and as a function of pressure and temperature, different pressure, different temperature, you can have the surface coverage. So, what I mean to say, by using the chemisorption study, you can find out the heat of chemisorption, right, or heat of adsorption, right. You can find out the effect of chemical reactive gas as a function of pressure or temperature, which can be used for further investigation in the reactor, right. So, initial investigation can be done in a micro reactor and then go in a larger reactor. So, dispersion we have talked, right, fractional dispersion, number of surface atom divided by total number of atom, right, percentage then multiplied. Chemabsorption we have seen, which can be written in terms of volume or in terms of number of molecules, right. So, molecule adsorb as a function of pressure. So, number of moles in the monolayer can be calculated, provided you know the stoichiometry, right. So, stoichiometry means whether it is associative chemabsorption or dissociative. So, hydrogen adsorb dissociatively on most of the surface, right. So, it means if hydrogen, one molecule of hydrogen you are taking, it splits into two atoms, right, and then it will cover on two metal sites. So, one hydrogen molecule will take two sides of that platinum metal, suppose, right. So, that is the stoichiometry here, and these are defined or can be calculated on different metals. So, platinum say hydrogen 1, right, the stoichiometric coefficient is 1, which is written here in terms of determination of this adsorption, that you are calculating the number of molecules which adsorb on the surface, right. And if I am saying that one molecule of nitrogen hydrogen adsorb dissociatively, it means that number of sites, if one molecule of the gas has adsorbed, it will cover two platinum sites, right. So, it means the total number of molecules, if I am calculating hydrogen adsorb, I will multiply to find out the number of platinum sites on the surface, right. So, that is the meaning, that to find out the number of platinum sites on the surface, because surface area ultimately we are calculating for the metal, not for the gas, right. So, we have to see that the molecule which adsorbs or chemisorbs, in what way it covers the surface of that species, right, active site, right. So, that is what the stoichiometry, and here if you have platinum. So, hydrogen metal, hydrogen, for hydrogen it is 1, for cobalt also it is 1. So, it is shown here 1:1 associative, right. Copper, nitrogen oxide on metal, so it is 0.5 dissociative, right. So, for hydrogen, if you have for this metal copper is there, for hydrogen it is poor hydrogen dissociation on the catalyst, right. The metal, if the hydrogen adsorption of copper is poor, right. So, poor hydrogen dissociation catalyst. So, generally for copper based catalyst, the hydrogen should not be used, right. Cobalt, if you have on, if you take carbon monoxide gas, if you take, then it is 1:1, right. CO can adsorb, one molecule of CO will adsorb on copper. Nickel, it is roughly 0.67, right, for N2 adsorption. For hydrogen it is 1 on nickel. For cobalt it is the formation of carbonyl, nickel carbonyl form. So, generally for nickel this should not be used, right, if you are calculating number of active sites. So, it will make nickel carbonyl with that, right, and that has been checked from the X-ray diffraction, right. Similarly, for rhodium it depends on the particle size also. So, if diameter is more than 2 nanometer, right. So, this is not used for rhodium generally, because it is oxidation gas, it can be used for treatment, but here if hydrogen it is 1, right. So, associative adsorption of hydrogen, and when it is carbon monoxide it is again 1, right. For less than 2 nanometer, that is the nanoparticles of that, it becomes a dissociative, right, and for this the information is not available, right. So, what I mean to say, the stoichiometry should be known on a priori, right, that whether the adsorption is associative or dissociative. So, that can be calculated based on the bond energy or binding energy, right, or then one can have the idea whether it is associative or dissociative chemisorption, and then calculate the number of active metals. So, once that is done, then you can find out the crystal size also, right. There are other methods also for determining the crystal size, right. X-ray diffraction can be used, electron microscopy can be used, right, TEM, transmission electron micrograph, high resolution transmission electron micrograph. So, these are the techniques by which you can find out the crystal size or particle size, right, and also that can be correlated with this, because you know the volume of a particle simply pi dp cube by 6, right, and surface area of particle, because we are talking of projected area, right. So, that is simply pi dp square. So, if you take these two ratio, so your dp is related to your or Vp volume of particle, if I write simply pi dp cube by 6, so pi dp cube by 6 is the volume. surface area of the particle, I am talking not VT. So, that is your pi dp square. So, I am talking a projected area, right. So, just if you take the SP by Vp, so this is pi dp square, right. So, pi dp square divided by pi dp cube and divide by 6. So, this becomes 6 upon dp, right. And since you are talking dispersion, number of metals which are exposed. So, we are taking total volume of the all particles and total volume of the surface area of those particles which are in a layer, and then that can be correlated like this, right. And dispersion we have already said. So, now if you look at the particle size and dispersion, they are interrelated, right. So, as the dispersion increase, your crystal size is decreasing, right. In one way, if you are able to make a nanoparticles, the particles will have a better dispersion, because it is the agglomeration of the particle, right. Crystals are agglomerated or particles are agglomerated, this crystal size is increasing, right, because of the agglomeration. And if that happens, if agglomerates, then definitely the dispersion will be poor, right, because it is a cluster of the particle now on one, right. So, gas absorbs only on one. So, number of sites are in one way reduced, right. So, that is the reason that you need to look at the well dispersed particles on the support. So, large surface area may be helpful in that creation of that kind of support. So, D is the fundamental parameter which is determined from Cammie-Jobson. dVs can be determined by using XRD and EM also. Type of the setup, if you look at it, is just kind of micro reactor basically, right, for which can be used for temperature program reduction, temperature program desorption, Cammie-Jobson, right. So, all these kind of studies can be done. You can take any chemical reactive gas, right. You can give a pulse through the syringe also, you can give pulse Cammie-Jobson, right. So, idea is that you are just after pretreatment of the sample, right, you give and this will be a function of temperature. So, Cammie-Jobson is very specific in action. So, at a given temperature, right, you give the pulses of hydrogen, right. Once the catalyst is well reduced, reduce catalyst and give the pulse of hydrogen, and then look at the response, right. How and you can have just the give the pulse of hydrogen, so it will Cammie-Job, right. So, allow it to Cammie-Job, right, and then you stop, right. Once you see that the Cammie-Jobson is complete, you will see that nothing gets adsorbed fast after that, right. So, now you just heat the sample gradually, right, and then just look at the response. So, at different temperature, because the surface metals may have the strong metal support interaction, right. Some of the metals which have the strong metal and support interaction, they will have weak Cammie-Jobson or the gas, right. So, they will release the gas faster or release the gas faster. But if there is a tuning between the metal and support, so there is strong Cammie-Jobson with the gas molecule may be there, right. So, that molecule will desorb at a higher temperature. So, by knowing these kind of plots, you can have the idea about the interaction of the metal with the support. So, how many types of the sites which are strongly binded, metal sites strongly binded with the support, and what number or what fractions are related to the weak binded, right, or intermediately binded. So, you can have some idea about the metal support interaction or what you call SMSI, right, strong metal support interaction or metal support interaction just. So, this kind of setup, if you look at, you give a pulse of any reactive gas which can be your hydrogen, oxygen or carbon monoxide, right. That is what generally most of the time we use, but sometimes N2O can also be used, right, Cammie-Jobson with nitrous oxide. This is your furnace, because it is a Cammie-Jobson. So, it can go up to 1000 degree centigrade, even 1200, right, from room temperature or ambient temperature to 1200. So, you can have a programmed reduction also, temperature programmed, right. The gas, this is the inlet cell, and gas from this comes to a detector. So, basically it is a TCD type detector here, because all these gases can be determined through thermal conductivity detector, right, a reference cell and then a measuring cell sample, right. So, you can have the signals something like this, right. So, you can have the peaks like this depending upon the concentration. So, it may be constant when nothing is Cammie-Jobbed, and it may decrease as I shown in the actual picture, because the chemisorption is taking place, the volume of the gas at the exit will decrease, right, and when the chemisorption is complete, then it will again be same. So, by adding all these peak areas, right, like this, you can find out that volume of the gas adsorbed, and this can be in the form of pulse, right, this can be in the form of step changes also, right. This is again the same, actually this is we say active surface area measurement technique, and here this is for catalyst surface area and dispersion calculation. So, basically the same figure, right. So, you have injected a given volume, right, at standard condition 100 microliter say syringe through syringe, right, of that gas, and then you have passed it into this, and TCD has measured the signal like this. So, it is constant initially, and then it decreased, and likewise, right here. So, you can just meet. So, for a given mass of the sample, say 1 gram, which has 10 weight percent, sorry 0.1 weight percent of platinum on gamma alumina. So, this is the catalyst, 0.1 weight percent platinum on gamma alumina, and its 1 gram mass of the catalyst has been taken, right, and heated at 423 Kelvin, right. So, adsorption of this hydrogen at 423 Kelvin, right, and then you can find out the area of these peaks. So, which is written here 3.75 peaks hydrogen, 4.5 peaks of oxygen. So, that is for different gases. So, pulse with hydrogen, then titrate with oxygen. So, how many molecules of hydrogen have been consumed during the process, you can find out. So, basically either this, and this is connected to the software, then directly you can find out the volume of the hydrogen gas which adsorbed on the surface, right. And once that is known, so you know this, that 1 gram molecule of the gas at a standard condition has 6.02 into 10 to the power 23 molecules, right. 1 gram of the gas had this much number of atoms, right. And so, there are some factor, packing factor, as I was talking earlier also, right, that is constant. So, generally that is not required at this, but basically knowing the number of molecules and volume, the same principle, same formula what we have discussed earlier, that the surface area, earlier I was talking physical surface area, now it is a chemical surface area. So, surface area of the metal, if I write like this, is equal to the volume of chemisorptive gas, say hydrogen adsorbed, right, divided by volume of the reference condition, right, multiplied by number of molecules which are available at standard condition, that is N0 6.02 into 10 to the power 23, and then it becomes 22,400 centimeter cube, right, and times the area of one molecule. So, basic principle remains the same, because now you know the chemisorption is on these sides, right. There is no adsorption on this side now. Bare surface, there is no chemisorption. So, here the gas will adsorb, here it will adsorb, here it will adsorb. So, we are just calculating, we are assuming that they are arranged in a closed pack array, right, and we are just talking a projected area of one molecule of hydrogen, and we know that one molecule of hydrogen molecule adsorbs on one metal species, one side. So, I can very easily find out the volume of the hydrogen gas which is adsorbed, right, and you know that at the standard condition of temperature, 1 gram mole of this has 22,400 volume, right, and which will have N0 or Avogadro number, right. So, in that, an area of one molecule of hydrogen, if you know, just like for nitrogen we said 16.2 angstrom square. So, you can find out the total area of the surface which is chemisorptive area, right. So, this method can be used for the determination of the surface area of the metal, that is active surface area, and in that active surface area how many metals are there, that can also be measured if you know what is the area of one metal, say platinum. So, one platinum atom has what is the area of that, and just you know the total area. So, number of atoms can also be found out, platinum atoms, active sites of platinum, right, that is used to determine the concentration of the active sites. So, the approach what we have discussed. So, just this is shown for copper nitrous oxide adsorption on copper, right. So, this takes two sides, right. So, two metal sides. So, adsorption, and this gives you something like this. So, because it is a chemical adsorption, right, so copper oxide forms. So, you have taken catalyst, pass it through the mass spectrometer, right, and then you determine the concentration of nitrous oxide, right, which is adsorbed on the surface. So, by difference, right. So, if you are given the step input, so you will get a peak like this and then constant, right, after that, and pulse it will increase. So, you can find out the response of that gas and you can use it for the determination. So, same what I have shown here in terms of this, right. Same thing here, pulse chemisorption, right, this is the carbon monoxide gas, right, CO, a pulse has been given. So, response is something like this. So, this simply shows that after this the chemisorption is over through the detector, this is the response from the detector, right. So, platinum on CO, so it is just the associative. So, platinum CO, carbon monoxide. So, difference in total peak area is nothing but the number of surface, right. So, this is what your chemisorption operators, which is generally known, right, for determination of the metal dispersion or the metal surface area, number of metal atoms, temperature program reduction approach is also similar, right. So, we can do that. So, these are just for a monolayer capacity, the per gram of platinum roughly 0.06 millimoles of this carbon monoxide gas chemisorbs. So, one this is the kind of signals with time for the pulse CO chemisorption on that platinum alumina catalyst. So, there are different type of responses can be obtained at different condition of temperature. So, you can have the activity correlation. So, whatever the pulse volume and the number of millimoles per gram of the catalyst, if you calculate. So, you can have a curve like this, millimole per gram as a function of volume when you injected the different pulse, right. So, the pulse volumes and you can find out the number of molecules. So, here it is now saturated, right. So, you increase the pulse volume, this is saturated. So, this is something what you are correlating, right, and that can be related with the surface area. So, you can find out what I said here. So, roughly 3 meter square per gram. So, the surface area of support is 200 meter square per gram, but the metal surface area will be low, right. So, that is why they are always in the disperse phase most of the time, but you have very high loading something like 60 or 70%, then there may be a question, right, that whether the metal is dispersed or not, which is the disperse phase, right. So, dispersion here is roughly 24%. So, this is just a typical result. How to find out, because sometimes the question may come that your support may also adsorb some of the gas, right, the chemisorption, suppose alumina. So, platinum on alumina. So, there may be a chemisorption. So, the calculation we will discuss next time. So, stop here today. Thank you.